We will really start this time the electro final event, and for that I will call Kevin Van Trem, our project coordinator. So we will introduce this meeting and the main developments within the electro project. So Kevin, the floor is yours.
Thank you. So welcome everybody. It's a great pleasure to be here. You see here in front of you a very proud coordinator of this project. I've coordinated many projects. I still do, but maybe this one is the one that I'm most proud of. I think you will also see some, impressive achievements. It all started 4 years ago, and we got a nice budget. But yeah, considering what we all promised, then this budget is even quite tight, I can imagine. So thanks to the contribution for especially the industrial partners, we were able to deliver. Yeah, and I think that's quite unique, especially in European projects where we achieved all the deliverables and we really made it happen what we promised. So. And I will try to summarize the main achievements here, and then we will go in more detail later on. This was a call where two other projects were also funded, Plastis, which was also on plastic waste conversion, also a pyrolysis option. And then we had plastic to olefins, was then going directly to an olefin route with a more catalytic option. You see here the full value chain. So what are the key differences with other projects? Well, here we really went for full electrification. So both the pyrolysis step and the steam cracking part are or can be fully electrified. We really start from real waste, so as dirty as it can get. And we tried, even with this dirtiest material, to make it work. And of course, we ran into challenges, but I think we were able to solve them. And next to that, we had very unique technologies. So the electrified plastic waste conversion process of Pryme, but in particular, the rotor dynamic reactor of Coolbrook, which is an incredibly unique reactor based on volumetric heating. And that was not operational when we started. So, of course, this is very uncertain when you start a project and the unit is not working. And then there were some initial tests, but it was just heating. So it was a big if, because I think industry was quite doubtful of will this ever work? Because a rotating reactor and steam cracking, coke formation, this sounds, a crazy idea. So you see here the 4 objectives. Really demonstration, large scale. So most European projects, they stay on bench scale. They never do something on high TRL level. Here we went to high TRL level. Both pyrolysis and also the Coolbrook plant, the people that will visit it, is high capacity units. We really tried to make also polymers again, starting from the plastic waste. So really closing the value chain, really showing circularity. And then, of course, we had the electrification, and we really assessed when will this concept, also from a CO2 point of view, be better than what is currently available. And that is not always the case. Well, I will be honest about that. It's not always the case that it's better than what's already available. It depends. And this is also something we learned. But electrification, coming with renewables, is really is a good step forward. Of course, the project will not stop here. So we achieved nice results. We demonstrated the pyrolysis technology. we demonstrated the electrical heating of a steam cracking reactor. We hope that in the future that this will be a sort of catalyst for further demonstration of this unit, further scale up, and I hear at least promising discussions that even higher TRL units are being considered either here, China, or in India. But who are we? Well, I'm very proud of this consortium. Of course, there's a very strong focus on Belgium. We have we have Ghent University as coordinator. We have AVGI as company. Engie Laborlec was there. Pryme is half Belgium, half Dutch. Then we had Coolbrook, which is half Finnish, half based in the Netherlands. AristEng, based in Luxembourg, but also with a Greek component, I can say. And of course, then I come to Greece, Aristotle University there. Our excellent group from Techno-economic Milan on modeling. We even had a partner in Korea because the waste that we were looking into, we basically want to look at that waste coming from everywhere in the world. It doesn't make sense to transport waste from Korea to here, but at least the composition of the waste is very different. The attitude of people, the sorting is really different in any country in the world. We had a Nature paper 1.5 weeks ago on pre-sorting and household sorting, if that makes sense or not. Here in the Netherlands, we did a study, and well, it has an effect, but it also depends on, in the end, if you are living in a dense region or a not so dense region, what the strategy for sorting should be. So you can imagine, this is different everywhere in the world. So you can live in the countryside in France, or you can live in Paris, and the optimal sorting strategy is different. So also the social science aspect was really critical in our project. And we had a group there from Ghent University who also did, I think, amazing work also on that aspect, because it's also responsibility of people. And Benkei was, of course, with Jean, very helpful and crucial in this project. It was a pleasure to work with Jean. He did an amazing job to push us, but in a friendly manner. That's what I really appreciate. Just checking, but I see that I missed VTT and Borealis. So we had also, I think, a very strong Finnish contribution in the end. Borealis also has a Finnish component, but also in here with the Austrian entity. And so Borealis really looked at the pyrolysis technology and the steam cracking ability, and see if that can work in a conventional furnace, because even that is not guaranteed. Do you want to put pyrolysis oils in your steam cracker today? Well, not always. I see Mark agreeing, so that's good. And we will try to illustrate that. And of course, VTT worked really on the pretreatment, so the Modix extruder. That's also the first step. You get waste. How do you, well, already remove a bit of halogens there? How do you feed it to your reactor? These are all continuous processes, and for most of us, this is obvious. The obvious that we will go for continuous processes because this is large scale. For pyrolysis technology, it's not so obvious. Well, it's not that obvious. Continuous feeding is challenging. There can be everything in waste. It's not a secret. I work also with Mura Technology. They found dog shit in the waste. That's it happens. People use their plastic bag. They put it in the waste bin. That's fed to your extruder. You can imagine. So you have a biomass component as well. let's call it biomass. But it is challenging. Yeah. So how did we tackle it? Well, 4 work packages. Yeah, people will go into it very deep. Work package 1 really on the pyrolysis part. Work package 2, classical steam cracking of the pyrolysis oils. Work package 3 is then the electrified conversion with Coolbrook. Work package 4 was the social aspect, but also the techno-economic evaluation. So we also looked at business cases. Yeah, we have an industry which is here, for example, here in Camelot today. We have an industry which is, for example, in Antwerp, in Finland. You have industry in France. But okay, if we have to now start from scratch, where would we end up? And I think quite interesting results came out of the project in that respect. Yeah? And at least for me, it's surprising. So if we start with the value chain, you see, starting with plastic waste, very detailed characterization. We went to the pretreatment with an extruder. Also there you have different options. But if you really want to go for a continuous process, then feeding with an extruder makes a lot of sense. And you can at least partly remove some of the halogens, as will be illustrated. Then we go to pyrolysis, and pyrolysis is a very robust technology, which in the end has a main product oil. Yeah. And that oil can be fed to a steam cracker. You also form a gas fraction and a solid fraction. We tried to look a bit at the valorization of those products for the gas, at least as possible. But okay, it also requires some further purification there. For the char, that is a challenge, and that also depends on which technology is actually, which company is actually doing this. What kind of permits do you have? If you are a company like Indaver, where you have a permit to use that char to combust it again, then it's relatively clear. But if you are in the middle of nowhere, then yeah, your char can even be a cost to get rid of it. So that really affects the business case. And of course, this needs to be optimized. So our objective is to feed it in a steam cracker. And you can do distillation, you can do upgrading, you can play with conditions. But in the end, you want to feed as much of this oils to a steam cracker. And that's also steam cracker dependent. Yeah? Some steam crackers can handle fractions up to 200 degrees Celsius, final boiling point. Some of them maybe 450. And some of them really can't handle anything because they're ethane crackers. Yeah? So it's not that obvious. Yeah? And now we go to the electrification. Yeah? And this means you need electricity. And the steam cracking plant is in the end a nuclear power plant in energy consumption. And we are closing our nuclear power plants, or maybe not. So this also changed during our project. We closing, not closing, keeping it open. Now in Belgium we are maybe running it ourselves or as a country. So that's also. But maybe it's not such a stupid idea to keep those things open, at least if you want to keep your industry in your location, because what you need, and that's clearly shown in our project, is you need to work your unit 8,000 hours per year. And this means stability and availability of utilities. And electricity is in this concept a utility. So if you don't have it, or you have to go like today, when you have to buy electricity from the grid, for example, now between 6 o'clock tonight and 9 o'clock tonight, at huge prices, this can really kill you. So it's not that obvious. So some things we learned a lot during this project, and that's why we had Engie helping us also with that part and making sure that we understand everything. But of course, you have to demonstrate. I believe in experiments. Voilà. As professors, we promise a lot. We promise the world. We can solve everything. But we do things on very small scale typically. So you have to demonstrate it on a large scale and may fail again, and then succeed. And I think that's also what happens here. You see where all the partners are situated over the project. And really, there were many interactions. Yeah. So all the partners were basically very much involved, and the dynamic was very good. I think we never had fights. Yeah. That's, I think, a good. I'm not a conflict person, but there was hardly any argument because also the progress was incredibly good. Yeah, and so it all started with the pretreatment. I think the main part there is halogen removal, and then here the modic extruder, and VTT will elaborate on that. Of course, the characterization and so on is really crucial. We did a lot of effort and to do that in a very detailed way. For the pyrolysis, of course, yeah, here it's really, we had the pilot plant at Ghent University of Pryme, but we also had the large-scale unit in Rotterdam. So that really allowed us to show that we can actually scale this up. We also looked at catalytic upgrading in that respect, and we developed also models for the pyrolysis part. So we did very fundamental work, but also very applied work. And then we went to the steam cracking part. And of course, we compared there really the conventional steam cracking process with this very novel technology of Coolbrook. And well, we made it work. Yeah, we didn't only used classical naphtha, but we did 100% pie oil, and that's a bit crazy, I would say. I think no steam cracking company would feed 100% pie oil to one of their furnaces. But we did it, and I think Tuomas will report a bit on the data. The unit is still there, well, so didn't explode. There's I think limited corrosion or something, so it can work. It can work, and it was a very big achievement. But just the fact that we were able to demonstrate this RDR is already a major achievement. Yeah, and that happens in time and within budget. Voila, within budget. This is always also not easy. And then the downstream. If you look at these feeds, they are contaminated. Well, it is what it is. Even if you do pre-treatment and so on, they will end up with oils out of spec. So the question is, how do you solve that, and what can you expect? What can you what can you do to force that a bit in the right direction? And well, we see that dilution helps. Well, I will summarize it like that. But if you look at the availability of these oils for the time being, you cannot feed 3 million tons anyway to a steam cracker because they're just not there, the oils. So for the time being, it's not a major issue. Yeah. And if you look at the economics, well, we really see that it's not that obvious to make a business case, especially if you want to go for 100% electrification. Electricity prices are just high. Yeah. So as long as you, as in the end, government cannot provide electricity in a competitive way, then this will be challenging. And I think that's also what countries are now realizing. If you want to make a big step in this area, then yeah, there will be a contribution from all of us. If we want to keep part of this industry here in Europe, it will come at a certain cost, which is spread over the whole society in the end. The other way is that we have no no process industry anymore. I think these are if you want to go for electrification. If you do electrification with renewable energy, you get low CO2 emissions. You can deliver the things what you get. I think today we cannot deny climate change. Voila. Today is probably the best day to say this. Voila. I rest my case. Okay, a week like this is the first time in my life, at least. But that shows that if we don't do anything, I think it will only get worse. Voila. It will only get worse. And that's a decision. And it is a decision that you have to make as society. okay, do we let it get worse or? And that's not an easy decision, but maybe for Belgium and the Netherlands, it's not too bad. Okay, today is bad, Mark, I agree. But yeah, I think if you really then go more to the south and if you see the temperatures now in France, 45 degrees, and then you will know what will happen in Spain over the summer, then yeah, I think we have to do something. So we will see. So now I will hand over the word to VTT, and they will walk you through their results of work package 1 primarily. But you see that all the partners will present their contribution. We didn't really go for the classical format where we walked you through work packages. I think it's nice to see all the partners and their contributions and that they can illustrate their highlights. I think all partners did an amazing job and they deserve to be also in the picture today at the end of the project. So thank you.
So hello, I'm Eetta Saarimäki and I'm from VTT Technological Research Center of Finland. So our objective was this pre-treatment, and it was one task in work package 1. And I want to explain now how we solved and how we did this in the project. So our target was to develop a novel extruder and in pilot scale, and it would be the pre-treatment for various and challenging mixed plastic waste materials for pyrolysis. And the halogen removal was targeted up to 95%. And how we did it, we built a completely new prototype for this system. And our new MODIX extruder consisted melt filtration, homogenization, compaction, and dehalogenization parts. And additionally, there was a neutralized gas scrubber in the system. And why this is important? Materials are difficult to get in pyrolyzable form, especially when they come in big pieces. They need a lot of pre-processing steps before they are able to be fed to the pyrolysis. And how our MODIX extruder works is it's space saving, and it has inline halogen removal gas scrubber system in there. And it was improving the quality for the pyrolysis in this stage. And we tested a lot of surrogates, which were made by VTT and also by Ghent University. And then we went to the real waste fractions, and these real waste fraction test trials I will tell you in this presentation. And the most important thing with this mixed plastic waste is to carry out the test in safe way. So we did quite a lot of efforts to make all the things during the trials and during the analysis, and so very safe way. And why MODIX? So as I explained, typically there are a lot of steps before melting the material. So the aim with this equipment is to reduce the process steps. Materials don't need to be grinded. They don't need to be compacted before melting. So that's easy. You can put big clumps of materials into our extruder. And the specialty in this is that it's also saving space, because it's not huge, many meter long extruder. It's a hollow rotor extruder, where you can put the system into very small area. And that's what it looks like in our pilot. As you can see, there are a lot of ventilation. Does this work? Okay, ventilation in this, and it's separately ventilated from our other pilot operations. So that's special room for this machine, because we work with very heterogeneous materials that even though we try to be safe, there can be surprises. And this is the simplified flow chart of this extruder. So we have now conveyor belt, and then the base Modix single screw extruder in there, and then we have this cascade system where the material goes to twin screw extruder. Now I can say that unfortunately we figured out that the output with that extruder is a bit at low side, and we have now ordered a new one that is taking more material from the Modix extruder, and the output will be bigger. This is only something up to 10 kilos per hour, but we can double or triple it with the new extruder. So the original idea was to move this whole system to Ghent and apply it to the pyrolysis system, but then we figured out that it's too risky in this project to move such equipment from one country to another. If something little happens, then we don't have anything anymore in this project. So we decided that we make the granulation in Finland and materials will be sent to the further stages. And here are the images of the equipment. And we have also a vacuum system where the gas scrubber takes the things out. I can go this quite quickly because I have explained it a few times. But then to the analysis. After the small lab scale tests and surrogates where we knew what materials were in there, we got the materials from Korea and Indonesia. Indonesian samples are called STOP, and they came from Borealis projects, and then Korean samples came from Ghent samples. And we did preliminary analysis for the materials, and none of the materials exceeded 1% of chlorine in there, mostly even lower. And the DSC showed that Korean samples were a mixture of polypropylene and polyethylene, and Indonesian samples contained also a small amount of polyester PET, most probably PET in there, but nothing very worried things came out from these preliminary feedstock tests. And this test was done actually after our test trials, when we had these top samples, and they really look like polyethylene, candy waste, paper, or plastic. And afterwards, we figured out that this candy plastic actually isn't polyethylene, polypropylene. It was PVDC, which is used in Asian countries. We don't use this in Europe, and that's why there was no suggestion or fear in advance that this kind of materials would have come to our trials, in our real trials. But as was talked, Korean samples were quite easy to process, and we used typical polyethylene, polypropylene temperatures, and from these we were able to take the little amounts of chlorine that were in the samples away due to this efficient gas scrubber. There was one bag which came to us, which was kind of clumps, which we didn't then compact at all, but the others were real waste, smelly, dirty, muddy, and they were easily compacted and filtered, and the granulation was very in good level. And then when we went to the Indonesian samples, we received 3 samples, and as I told, the analysis was done only for the 1 sample, and the first test trials went very nice. We compacted it and we filtered it, and then we figured out that it's very sticky, almost rubbery-like, and then we moved the filter because we had this changeable filter. We had to change the filter opening to 900, but still that was able to be done. But when we started the second pack, which looks almost identical, there wasn't any difference in there, and the material started to degrade. And the gas scrubber liquids turned black. So our personnel, who is very skilled there, realized there's something wrong, completely wrong with this material. It's not the one that we were thinking of, and the material the tests were stopped from that material. So we did XRF tests, and the chlorine which was detected in Korean samples only had 0.05% in the remained samples. So it's very, very low level of chlorine. As you see the scale here, it's only 0.2% here at the maximum. But when we went to the Indonesian samples, we had made hot pressed samples so that we get bigger area for XRF mixed waste, not just from one piece. And we figured out that some of the samples contained almost 10%. And these were the preliminary tests from the samples. But after we have treated them with MODIX, this is the stock 1 sample. The reduction for the chlorine was 93%. So I think that's the quite good result based on based on the materials and difficultiness that we faced here. And here is the stock 2 sample. As can be seen, the preliminary test for even washed samples, as here, to make sure that it's not from sea salt. We're very, very afraid this increases the amount of chlorine in PVC, so it has to be PVDC. And we got few samples from the studied system, and we were able to decrease the amount of chlorine, but this kind of material is not useful for pyrolysis in any mean. So the conclusion and summary about our work is that we were able to manufacture the system which pre-treats municipal waste and remove impurities from the feedstock. And we successfully built and demonstrated the MODEX 2 technology for the effective impurity removal from mixed plastic waste. And we were able to make safe and more stable feedstock for pyrolysis processes for future in this project. Thank you very much.
The next presentation is from Pryme. I think it will be Azd. But we'll start. Azd, the floor is yours.
Thank you very much. Morning, everyone. The supply chain of the electric project has already been explained very well. And for the work package number 1, where we have worked closely with other partners like UGent, where they have mainly worked on the characterization of the feedstock as well as the pyrolysis oil and the char for the demonstration and process in pilot plant. We have our pilot plant in LCT in Ghent, and for the removal of the impurity, already Eetta has explained the MODEX extruder, and for the optimization of the process, we have worked closely with Thessaloniki University as well as Polimi. So for Polimi, they worked on the optimization tool, and for Thessaloniki, we have worked together on in situ, ex situ, catalytic upgrading of the pyrolysis oil and for processing of the feedstock. Lastly, we have the demo plant in Rotterdam, where we're gonna show first like the place where our pilot plant was situated in Technology Park, and the demo plant, which is the RL7, which is in Rotterdam. In the next, we're gonna show a video. I think we can play directly.
Let's go to the next.
So we have seen first the demo plant, which is plus 16,000 ton per year DRL7 plant in Rotterdam, and the next one it was the pilot plant in Technology Park. So here I'm gonna shed a light on the major achievements which we have done. First of all, to check the replicability, we have processed lots of feedstocks, because when we are moving from virgin plastic and go to the reality and processing, as has been already mentioned by Kevin and Eetta, we have found lots of impurity with different quantity and quality. For this reason, we have processed feedstocks from Europe, from Asia, like from Indonesia, from Korea, and from Belgium, the Netherlands, from Germany. So we have seen lots of surprises. So I can say the feedstock is just like black box. You don't really know upfront what it is. For this reason, I think characterization is quite important for not only the quality of the bio-oil, but it's quite helpful and essential for checking the quality of the feedstock, to optimize the process, as well as for avoiding maybe some difficulties in processing or sometimes unsafe situations. In the next, like we have done in collaboration with Thessaloniki work, and for that one, we started from lab scale for using catalyst for processing feedstocks. So based on the initial results, we decided to go for the next step, which is using pilot plant for processing feedstocks. And usually for scaling up, we have limitation, we have constraints. Like if we are using lab scale or very small scale micropyrolyzer, in which we say, okay, we can use 50% catalyst to process the feedstock. When we are talking about demo plant with 16,000 ton per year, it's not visible. So we have to limit this percentage, for instance, to 2-3% maximum. And based on the results, we go afterwards to say, okay, it does have a huge effect or it doesn't have. So for scaling up, we went stepwisely from lab scale, pilot scale, and we ended up at the end for not going for in situ, for instance, catalyst for the demo plant. Here, I'm just showing part, it's like tip of the iceberg of all of these analytical work and experimental work which we have done. For instance, we have done here the using NM, which refers to the catalyst which we have used, and here the GC time GC analysis of this pyrolysis oil, and here you can see it's like zigzagging. And the reason why it's going up and down, because whenever we have mixture of polypropylene and polyethylene, the same carbon number compound from polypropylene, which is highly branched, has different boiling point compared with polyethylene-based pyrolysis oil. For the next, we have done as well for the purification in collaboration with VTT. Instead of going directly for processing the feedstock, we have sent several feedstock, including surrogate feedstock, which has been prepared by LCT UGent, as well as Indonesian feedstock, Korean feedstock, and in Finland, in VTT, they have pre-processed, purified, granulated, and it went back to Ghent, where we have done the processing of these granules of the waste plastic. So here we can see the limitation, for instance, for even for treatment or purification, we cannot claim, okay, we can have feedstock with 10% of PVC. There should be always a standardized way for checking the quality of the feedstock, controlling the quality of the feedstock, and afterward, after doing this process and producing the pyrolysis oil, we can link the quality of the pyoil to the quality of the feedstock. Because at the end, if we are producing like pyoil off spec, it's not only useless, we have to pay like for getting rid of the off specification pyrolysis oil. So it's like full chain from A to Z. Here we go for another analysis, like using the surrogate feedstock, which is in a controlled manner, like Daniel from LCT has prepared this, and like for impurity, like biomass, for PVC, for other types of impurity, it has been blended, mixed, granulated, and afterward we checked the migration of this impurity from the feedstock all the way to both of the char or the solid residuals and for the pyrolysis oil. Here we go for the TRL7 demo plant, and I would like to invite Dominique,
thank you,
CTO of Pryme. Please go ahead.
So sadly, we could not host the meeting today in Rotterdam. Otherwise, you could all have seen the pilot plant or the demonstration plant in real life. That's why we included the video. But you can really see the, let's say, the size of the equipment, how it is built in Rotterdam. And first of all, some of the results which we achieved there is that the results which were achieved by Azd at the TRL5 unit in Ghent, we compared them, of course, against similar feedstock run in the TRL7 plant, and we saw very comparable results. So I think that is very, very positive to achieve that. We did commission the unit early 2024, and we have conducted multiple demonstration runs. In total, over 90 runs that we conducted over early 2024 till now, which total about 1,400 tons of pyoil. I will come later more on that because it's a nice number, but actually for the plant which we have built, the number is actually small because we want to produce kilotons per year and not 1.4 kilotons. But that was the result which we were able to achieve. So we did demonstrate the entire process from the beginning, being, you have seen this truck unloading. So we had a walking floor unloading system where in both material was unloaded via screws. It's then fed into the two industrial size extruders, and we were able to fully demonstrate the electrified process through the electrified reactor into the pyrolysis oil, the non-condensable gas, and the char, which was free flowing. You see there a picture of that. And we did deliver multiple samples in smaller quantities to the University of Ghent and other partners. But also, as already indicated in the introduction of Kevin, we have delivered multiple IBCs with pyoil to Coolbrook for actually conducting this real RDR demonstration with pyoil. We did demonstrate also, which was part of the objectives, two industrial size extruders, a twin and a single screw extruder. We compared them on multiple parameters. Key things I can say is that we were able to achieve temperatures up to 350 degrees with the extruders, and the specific energy consumption of the two extruders was much more in benefit of the twin screw, about 0.2 kilowatt hours per kilogram versus maybe 0.4 for the single screw extruder. Also, stability-wise, the twin screw was much more stable. So as a conclusion from that, we would more opt for a twin screw extruder for capacity, stability, energy consumption, and good dehalogenation possibilities. Feedstocks, multiple feedstocks were tested there. Of course, we did not test feedstocks from Korea or Indonesia because the quantities and that was just too complex to do, but we did test multiple feedstocks from Belgium, the Netherlands, and Germany on the plant. You will see also on the next slide that as we did more feedstock screening and more adequate selection of feedstocks for the demonstration plant, we were also able to improve the quality and the yield significantly due to feedstock selection. We also successfully tested an abrasive material inside our reactor, because one of the downsides is that the solid residue or the char which you produce also can cause scaling and hence heat transfer loss or capacity loss inside your reactor. results of that are also further implemented in the deliverable documents. And then, of course, we have learned a lot from 2024 till now, and we have actually improved and optimized our process and actually have overcome a lot of challenges. Final boiling point, as we have a single cut pyrolysis oil, our final boiling point is high for this process, around 600 degrees. In order to mitigate that and try to reduce it, we did implement a project with an internal recycle, but we were not able to commission that eventually and test that. So that is one of the items which we were not able to achieve the effective testing of that. Further, all of the Horizon TRL7 demonstration tasks were finalized, except then that previous FBP improvement run. We did face many technical and operational challenges, and we had a dedicated focus on all the key challenges and tried to work them down, and therefore actually improved step by step, and that had an impact, of course, also on the uptime. Kevin mentioned that for chemical processing, you want very high uptimes per year to have it economically viable. We are, of course, with the asset in Rotterdam, we have a large team there. The plant needs to also produce a lot of oil in order to be economically viable, and I will get there on my next slide to that point as well. So just some high-level results from oil. The different colors are just different feedstocks, and you see in timeline over different demonstration runs, the oil yield, we were able to increase it up to values of 75 to 80% at the TRL7 demonstration plant, and the char yield also dropped significantly. That has, of course, a lot to do with the feedstock selection, but as Kevin mentioned, we do not have an incinerator for our char on our site. So for Pryme, the char was actually a challenge to dispose of, to get rid of, because it is not what many might, or what some might claim, it is not yet a product, it's not yet REACH registered, so it's a waste. And it's a waste which is not that easy to get rid of, because it's the digestion of everything, all the impurities, metals, it all gets into that char stream. So it is actually a significant cost and impact on the business case to get rid of that. Then, of course, we faced a lot of issues which we tried to tackle along the road. And that, of course, resulted in lower reliability, poor reliability, which we didn't expect or want. And therefore, the oil volumes, they were far below the expectations. And all of that was mainly linked to our reactor, which 97% of our downtime was linked to the reactor unreliability, mainly to sealing issues and also some electrical heating circuits that sometimes malfunctioned. And therefore, because we had a large organization, the cash burn was high. We investigated to replace the reactor actually by an upgrade, looking for something which was more suitable, but were unable to find such a reactor, and it was also not supported anymore by our investors. So by the end of March, when we had another failure of one of these elements, this discharge valve on the reactor, the difficult decision was actually taken that we had to stop and halt the operations at Rotterdam. And this also with limited investor willingness, because the results were not there as we hoped so. And we did prove the process, but maybe not at the uptime required. And that's where maybe one of the examples that, sometimes you win, sometimes you fail, but we hope that there can be a continued story also from the learnings of this. So at this moment, Pryme will not continue to develop own technology and build new own Pryme plants. We will finalize our R&D activities with Horizon, and that will end by the end of this project. But our TRL7 demonstration plant will be shut down, and we will see how we can reorient our company if possible. And linked to that, maybe a final statement is also linked to the business case, because the EU regulation plays a very big part in this. As long as there is no fixed PPWR implementation timeline and with mandated percentages, recycled content, and very clear secondary legislation how to implement it. There will remain uncertainty for getting a fixed business case. That will be affecting investors to put their money on the table. And we see that not only with ourselves, but we see Plastic Energy being here on site, being under administration, Quanta Fuel being shut down. A lot of the chemical recycling business in not only in Europe, because also Freeport in the US, they had to close down a large plant in Ohio due to EPA issues. So chemical recycling is suffering. And of course, technology is important, but it's important that there is a strong EU regulation that supports business cases and that companies like ourselves or others have the chance to make a business case and keep investing in trying to make this work, because otherwise it will just, be a lot of effort and then die off. So that was my last word, so thank you.
Okay, thank you. We'll go now to the next presentation from Ghent side. So I invite you, Kevin, again, to present this summary.
Yeah. So you will see that as Ghent University, we were active in almost all the work packages, and also very active in the social science aspect. And indeed, that was also a lecture yesterday of Kim Rahart at the Catalytic event. And in the end, the conclusion is and was, without legislation, this will not happen. Without a clear legislation, then it's very difficult to have a business case. So now with mass balance at least being considered, and I think that on the long run, okay, everything is now happening. As you know, Ghent University is also advising the Commission in that respect on the new legislation and new to PPWR. So we see movement in the right direction, but it goes slow, and maybe a bit too slow, but legislation will come. But probably I think it will be more by 2028 or 2029 than next year, in my opinion. Yeah. And that's it's concerning. But without a clear legislation, it's very difficult to come up with solutions. Yeah. And that holds for any recycling technology. You see the same thing with mechanical recycling and dissolution recycling. So it holds for many of these technologies, and they're basically also complementary. Pyrolysis is now, I think, very suitable for polyolefinic waste feeds. You have dissolution recycling, which is then better for others. So, but basically, this is what they have in common. Without a clear legislation, they all have difficulties to compete with cheaper virgin materials, especially coming in from China and the Middle East. And so we, as Ghent University, of course, very active in work package 1, work package 2, and work package 3 with the pre-treatment and the material characterization. So I think Daniel sweated a lot on this topic. Getting these compositions in detail is not easy. Voila, it's a lot of work. You need to do multiple techniques, TGA, DSC, ideally also NMR, elemental composition. So you have to look at impurity, ICP-OES, combustion, ion chromatography for the halogens, CNHS and O, and also, well, if you can, pyrolysis, GCMS, and so much more. So this is really energy intensive, at least from the people that have to do it. Yeah. And waste is always different. Yeah. Every waste that you start from, it will be slightly different. And this really matters. Well, what you put in not always comes out. But most of it comes out. but something can stay inside the reactor, and that's basically affected by these impurities. So we invested a lot of time on these analytical solutions and applied it to Korean waste, Belgian waste from the Netherlands, and from everywhere where we could get access to. Yeah. And of course, we helped Pryme a lot with characterizing the oils that were produced in their pilot unit, which was on our premises. We looked at the oil with comprehensive 2DGC, with different detectors, FID, MS, AED, SCD, NCD, everything what you can get access to. We characterized the gases with refinery gas analyzers and so much more. Yeah. So a lot of oils were produced. I think we had almost 100 samples, and they were all now characterized with GC times GC. So we have a huge database of oils and also the starting materials. So it's a very unique data set, which is on its own already very valuable in my opinion. And as you can see, well, this is the result of a GC times GC chromatogram and an integration. So this is now just primarily the hydrocarbon fraction, but you see many different classes of components, many different classes. And getting this type of information is takes a lot of work, takes good analytical development methods, and even then there is uncertainty. Yeah. But you see that this is around 3 different types of waste coming from Korea. That the distributions they are very different. Yeah. And you see, for example, peaks around the C9 part, and this is basically the trimer of propylene. Yeah. So this all shows that these feeds already contain, the starting waste is already high in polypropylene content. Yeah. And that always comes back in all these oils. But you see that distribution, this is carbon number C75. So if you feed this to a steam cracker, this will not evaporate. So this already shows that in a very simple slide with one analysis that, okay, this is not that obvious. Yeah. And then you have components like, for example, diolefinic components. And then you can already imagine that they have the tendency to polymerize, and that's also related to fouling. Yeah? So you can also cut them. You can make a cut, 450 cut, you can make a 350 cut, and so on, and then you can decide what do I do with this kind of fractions. And of course, with, for example, the new legislation in place for, or the directive for PET bottles, the boiling point is there even mentioned. What can your cracker handle, or what? So a final boiling point can determine recycled content. And of course, that's steam cracker dependent, but it plays a role in what you can allocate from a mass balance point of view. Yeah. What you see in these oils is that, well, always a lot of olefins. Yeah, always a lot of olefins. And in this case, even large amounts of isoolefins, because really this really was a polypropylene-rich feed. If you have a polyethylene-rich feed, then this would move more to the alpha olefins type of feed, and it would have less of these components. But these are all things we studied. And olefins are, in the end, not desired in a steam cracker. So typically there's a spec of around 2-8%. So you see that you will not meet that, and a potential solution is there, hydrotreatment. But again, that brings extra cost. So if you would be able to avoid that, that is not that straightforward. Yeah. And you see the boiling ranges. So this means that some of the heavy part will end up in the fuel pool, and which then, according to the legislation, fuel exempt. Fuel will not count as recycled content, so this all has effect on business cases. Yeah. We also looked a lot at the steam cracking part, and we made different blends of different oils, so of the light fraction, the heavy, and the full range. And from a yield point of view, you see that the differences in the end, if you look at ethylene yield with 25% blend, then it's not so different. Yeah, it's not so different than compared to fossil naphtha. Of course, it's a bit dominated by the fossil naphtha, but in the end, the yields differences are not huge. Yeah? And this is not so surprising if you look at the chemistry in the end. But what is the challenge there? It's more on the fouling. Yeah, the fouling is really then the challenging part. Yeah? And where will the fouling happen? Well, what we see is, and but to our surprise, it's not so much the reactor. Voila. It's not so much the reactor. It is the convection section and the TLE. Yeah? There the fouling rates are really substantially higher, yeah? Depending on the feed. And that's of course one of the challenges, because it's really depending on the feed. So which waste you put in really makes an enormous input on the fouling you will get in your convection section and also in your TLE. Yeah? So composition is crucial, and you need very advanced techniques to get compositional information. So, and I think this project really helped to get a very good database of feedstocks, but also fouling rates, to get at least compositional understanding, crucial and whatnot. Yeah. And you see that if you look at specs, that for example olefin content, okay, you can get there with blending. The same with nitrogen and oxygen and metal content. So, but for the halogens, it can even then remain a challenge. It really depends on the material, if you can reach the halogen spec, even with blending, to a very low degree. So that's why dehalogenation is really crucial. Yeah. Another aspect that we invested a lot of work in, and I look at Mike now, he did amazing simulations. Voila, I think he overheated our supercomputers in Ghent like hell, because he really made this real full 3D simulations of this RDR unit, of the initial version of the pilot unit, and you just see the mesh. Voila. Just look at the mesh, the level of detail that you need. I always wanted to become an architect when I was a bit younger, but this is like, it's almost like a piece of art. And you really see here the design, and so the nozzle, the impeller, the diffuser, and so you will get the shock waves here. We were all able to simulate that in full 3D, or in at least part of the unit, depending on how heavy we wanted to make these simulations. But some of the simulations take 4 months to run on a supercomputer, and we have one of the best supercomputers, at least in Europe. But more importantly, the results agree with what is reported by or measured by Pryme. So simulations are nice, and they can be super heavy, but okay, so you see, if you look at the temperature measurements and the simulation results, then depending on, you see here, the models that were applied, then we get a decent agreement with the temperature increase measured in the reactor. And these are non-reactive data. And then, of course, it's easier to get these temperature measurements. And you see that the turbulence model plays also a role. So the model properties, what you select, is crucial to get the agreement. So we really developed dedicated models for 3D, but also for the seam cracking part. Yeah, and you would say steam cracking, well, has been done for 50, 60 years. Models are there, Spyro is there, COSIM is there. Why would you need something new? Well, just look at all these olefins. And these olefins are not present, not in this quantity, but also in structure, in classical fossil feeds. They're simply not in there. Well, and that makes a difference. Yeah? So especially also if you want to relate this also to fouling. Fouling in the convection section and fouling in the TLE and fouling in the radiant section. Then this really plays a crucial role. So we had Tuomas there doing this work intensively and generating a new model. And you can see it here that if you would use a classical fossil-based model, we'd end up here, and with the new model, we are a lot closer to the experimental data for cracking these pyrolysis wells. Yeah. So we have a major improvement there. So last, we also did full 3D simulations of the RDR unit, and these are now results for ethane cracking, but we were able to also look at coke formation. Yeah. And our models account for coke formation, and you see the coke formation here. So you see that where coke formation can be an issue, there will be coke formation. Yeah? But coke formation will be less because it's in the end temperature dependent. Yeah? It's exponentially depending on the temperature. And the temperature at the walls is just lower. But you see that the temperature also high at the rotor and the stator, but there you have so much shear stress that the coke cannot adhere. And that's also confirmed by the experimental data we have. So the big concern we had related to coke formation in the RDR unit, well, the units had incredible operation times. So it works. And I think that was the, I cannot highlight how important that is, that you can make this technology work for a substantial time. And that coke formation is not the main issue that we expected it to be. Yeah. So that's a very, very nice result we achieved. And well, we had a discussion before we started this meeting, and you said, okay, this pilot plant has the highest operating hours that probably of all the pilots that have ever been here on this campus. And that proves the point. That proves the point of having a pilot, because there were so much concerns about this part, especially the coking part. So I think that's a really incredible achievement. And, so thanks for the people from Coolbrook because it's not easy. It also depends on people. So technology development also depends on people. So thanks for realizing this. Yeah.
Okay, so the next presentation is from the Aristotle University of Thessaloniki with the catalytic upgrading of Pyro.
So I'm Petros Soldatos from Aristotle University. Aristotle University participated in eLECTRO with two departments, the chemistry department and the chemical engineering department, and our goal more or less was to develop some catalytic, let's say, systems to upgrade the plastic waste pyrolysis oils. These efforts resulted in the successful completion of two deliverables about initial and final results in catalytic upgrading, and one milestone about the process and catalyst selection for exit upgrading of plastic pyrolysis oils. In brief, let me describe our task. So first of all, we needed to improve the oil quality of the crude plastic waste pyrolysis oils, and actually we wanted to maximize the light and naphtha fraction, the C5 to C12 fraction, and to do that we also needed to minimize overcracking to gases, because we want to preserve as much liquid oil as possible. To do that, we have screened and optimized various catalysts. We have used a lot of catalysts, and we have also assessed some catalytic matters like stability, regeneration, deactivation of catalytic materials, etc. From a process perspective, we have divided our work in two major, let's say, pathways: the in-situ catalytic upgrading, where the plastic pyrolysis and the catalytic upgrading of plastic vapors mainly takes place in a single reactor, and the ex-situ or the downstream catalytic upgrading, where the upgrading takes place in a separate reactor under milder conditions, and we are using the crude pyrolysis oil, the thermal produced pyrolysis oil. So as I said, we have used a lot of zeolite, mainly zeolitic catalysts. We have modified them, we have optimized them, and of course we were also working on detailed characterization because we want to link the main catalytic properties to the products and see what are the properties that are mainly affecting our products. And to do that, we also needed to develop a lot the analytics. We have worked a lot. We have developed some protocols. We have developed some in-house methods. We have used also specific analysis because in total, plastic pyrolysis products, as described earlier, are very complex. So this was also a major part of our work. And we have also used a variety of reactors, ranging from fixed bed reactors, classic batch reactors, flow reactors, in a very broad range of temperatures and pressures. And of course, we have participated in broader activities within the eLECTRO scope. So some of our key results, first of all, for the in-situ catalytic part, we have screened mainly zeolite topologies, commercially available catalysts, and this is a fraction of all the materials we have tested actually. The zeolites we found out are working the best are actually ZN5 and beta zeolites. Both of them could 100% crack the pyrolysis waxes, the heavy pyrolysis fraction, but the main difference between them is the selectivity. So ZN5 is a very selective catalyst to gases. We get very high propylene and butenes yield, while beta zeolite is very selective to naphtha, to the C5 to C12 fraction, and we were able to achieve up to 65% in the in-situ catalytic upgrading of the naphtha fraction. So another very important parameter is the naphtha composition, the pyrolysis oil composition. More or less, we found out that during catalytic cracking, with any catalyst we used or any topology, we have a very high amount of olefins in the resultant oil, which is expected because we're talking about catalytic cracking of hydrocarbons mainly. So we had a very high olefinic content, but we have pretty low to moderate aromatic content. Also, aromatic content really depends on the condition of pyrolysis, and we can really play a little bit with it. It is really dependent on the conditions and the catalytic properties. For example, catalyst acidity plays a major role in the aromatic content for the in-situ catalytic upgrading at least. The next thing we did is we evaluated some cheap alternative catalysts with the potential for a scale-up. Of them, we were mainly focused on some natural zeolites obtained from a Greek company. Some of them were treated, some of them were untreated. The treated zeolites mainly showed a major improvement in wax cracking when we used polyethylene as feed, and relatively high naphtha yields ranging from 30 up to close to 50%, which were pretty surprising for us. These materials, the gas content was really low, and not only we could crack the heavy waxes towards the desirable naphtha fraction, but we're also able to minimize the very heavy compounds. The compounds, for example, with final boiling point above 500 degrees. So you can see that in the thermal pyrolysis of polyethylene, these compounds were more than 50% of the total products, while when we used the most active natural material, natural zeolite, this went lower to 20%. Of course, the pyrolysis oil composition is still mainly olefinic. And the next thing we did was we regenerated and reused the best sample, and we saw that it can really work after some regeneration cycles, and the activity pretty much remains the same as the first material. For the ex-situ part, we have divided our work with model compounds and with the real oil provided from Pryme. We have mainly worked with batch reactors and fixed bed flow reactor. And for the ex-situ part, we didn't only want to see what's the catalyst effect. Of course, we have tested some zeolites here as well, just to see which one is working better for our reaction. But we also wanted to see what's the effect of operating conditions in the upgrading of oils. So for this one, we have used different temperatures, different product times, different pressures. We have moved the reaction regime from gas to liquid phase. Also have used reductive atmosphere or inert atmosphere as well. So for the model compounds, first of all, we found out that at milder conditions we used in the XC to catalytic cracking, the ZSM5 is a very good catalyst. It's very stable, and also it can provide, it has the required acidity to effectively crack the oil at low temperature. Another thing we found out was that in the gas phase, the cracking was really intensive. This temperature was around 300 degrees Celsius, I think it was 290, with very high conversion of the model compounds. However, we have pretty high gas yields. On the other hand, high pressure operation gives us lower conversion, but very high naphtha selectivity and high naphtha yields as well, depending on the feedstock. Another thing that was really important in this study was what's the effect of operating conditions of naphtha composition. How does it affect the naphtha? The first thing we observed, of course, is that when we used the model normal hexadecane, normal paraffin as feedstock, we obtained higher paraffinic content in the resultant naphtha, while when we use the alpha olefin, the hexadecene, we get more olefins. But this changes for both feeds when we increase the pressure. So when we use high pressure and we move the reaction regime towards the liquid phase, we are actually enhancing the hydride transfer reaction. So we are basically enhancing the isonormal paraffins in the resultant oils without adding an external source of hydrogen. Of course, this comes with a trade-off. We have also increased aromatics and some dearomatics and other precursors, but it's something that someone should consider when selecting the final technology. Next thing, we moved on with the real oil. We selected the batch reactor because it showed the best results using the model compounds. And we followed the same philosophy. We started at 300 degrees. However, at 300, we saw that the temperature was relatively low to crack the real oil. It is something expected. I mean, working with model compounds and the real oil is something totally different. Then we need to increase a little bit the temperature, and at 350 we've did very nice results. We managed to increase the naphtha yield in the upgraded oil by more than 80%. And it's not only about the naphtha, we also managed to decrease the final boiling point of the products, and by these results we also succeeded in the milestone. This was something very important because we have this milestone criteria here. So we obtained a total products up to C15 in the final oil. These were more than 60%. And also we minimized the very heavy products, the ones with final boiling point above 500 degrees to less than 5% in the upgraded oil. So then we reused this catalyst in the second and third experiment. We want to see how and if the catalyst is deactivated. More or less, it is deactivated actually. The naphtha yield drops by 60 and 80% in the second and third reuse. However, after some analysis on the catalyst itself, we found out that this deactivation isn't irreversible. It's not because of the metal content, for example, of the oil. It's mainly due to coke formation. And actually, it's mainly due to soft coke formation, mainly adsorbed species. So after calcining the catalyst, after generating the catalyst, burning off the coke, we managed to totally restore its activity, and we obtained exactly identical results as the fresh material. Another thing we did, it was, as I said earlier, more or less the products are olefinic, so we also worked a little bit with mild hydro treatment. For this one, we used metal-modified zeolites, of course, under reductive atmosphere. More or less under all conditions and all the oils we tested, we managed to successfully hydrogenate the oils totally. We minimized the olefinic content actually, as you can see here from the NMR graphs. We totally eliminate the olefinic signals. However, we couldn't crack significantly the oil because we used very mild conditions. Actually, for hydrocracking, you need 350 or 400 degrees, but it is an option if someone wants to the oil as well. We have also participated in other supporting activities. We have obtained some thermal pyrology data, and we delivered this data to Polimi to help them a little bit with their modeling tasks. Also, we have participated in collaboration with Pryme and UGent in char characterization, pyrolysis char. We have also explored some potential valorization pathways. We have treated a little bit the char to get rid of the most concerning, let's say, compounds such as chlorine, and we have also very nice results in this matter as well. So for the conclusions, of course, catalytic pyrolysis, it is a very promising method to produce naphtha-rich hydrocarbons using tailored or specific catalyst. Zeolites, and especially a ZSM5 zeolite, could be a promising catalyst as well for the mild exit or downstream upgrading of the crude pyrolysis, thermally produced pyrolysis oil, in order to maximize the naphtha products. The naphtha yield and the paraffin to olefin ratio can be both tuned by adjusting just the fluid phase or reactor hydrodynamics without adding an external source of hydrogen. And of course, we think that, that this path, using a continuous flow or a semi-batch reactor operating under pressure in the liquid phase, shows a very high potential for real mixed plastic waste pyrolysis oils upgrading to naphtha. So thank you all.
Okay, so we will start again this event with first, for this second session of presentations, the Polimi presentations. So Chiara just can come to present the kinetic modeling and the reaction optimization.
Okay, so I will present the work on Polimi, and in particular, I want to also mention the great work provided and performed by Andrea Locaspi in the context of this project. And so, okay. Basically, when we talk about pyrolysis modeling for plastic polymers, it is actually, we can define it a nightmare, in the sense that it is an incredibly complex process that involves multiple phases. So, and also, and it involves complex fluid dynamics, complex and multiple phases, multiple reactants. So our approach was starting to simplify the problem and trying to decouple the different difficulties that had to be managed. In particular, we started with the... Sorry, I'm trying. Okay. Okay, so our goal was the development of a general framework to model plastic pyrolysis, and in particular, the purpose and the main objective of the modeling was the actual possibility of optimize the reactor operation and possible design. In particular, we started to focus on the condensed phase modeling for single polymers, and we managed to model and simulate the condensed phase degradation of the main polymers which constitute the plastic waste. So polyethylene, polypropylene, polystyrene, PET, and PVC. And in particular, we were able to do that and validate our result in terms of polymer weight loss and also product speciation. So our goal was actually create some models that were able to reproduce the expected product distribution, and in this way also to tune the process operating condition towards the desired product distribution. So, as I said, we started with the condensed phase, and thanks to the selection, the models we have actually developed, we are able basically to reproduce the condensed phase degradation of maybe the 90% of the plastic waste. In particular, how to model, how to do this, how to model the condensed phase degradation of single polymers. We started with single polymers since of course, there are a lot of more data available in order to validate these models, which are based on a classical radical decomposition mechanism. So with initiation, propagation, and termination reaction. I will not enter the details of this modeling, but what I want to point out is that these models are semi-detailed, but there's the possibility to further reduce them up to multi-step models of just 5 species and 10 reactions, representative of the whole scenario, and which makes them possible to be coupled to very computationally expensive applications such as CFD. In this case, you can see this is a totally general decomposition pathway that can be generalized to polyolefins and also to PVC. Of course, in the case of PVC, there's also a strong parallel mechanism about the side group reactions, since in that case, chlorine is the more reactive component. So there's also molecular specific pathways for PVC and also for PET that account, of course, for the syn elimination and the production of the carboxylic acid. And these are the results, very promising, that we obtained. This is just the tip of the iceberg of the work performed by Andrea. And so you can see our models successfully can reproduce the degradation of, in this case, just for the sake of example, I reproduce polyethylene, polypropylene, and polyethylene terephthalates. And for different heating rates, the polymer weight loss can be successfully reproduced. And not only that, also the product speciation. We are able to capture the wide carbon products that are produced and released from the degradation of polymers, in this case, polypropylene. And clearly, the cooperation with other partners of this project, such as the Thessaloniki University, was exceptional, because in this case, we were able also to use their data from micropyrolysers, and we could actually validate our models and the product distribution we could obtain for also polystyrene, polyethylene, and PET, with very promising results. And I also want to point out that, for instance, for PET, among the different models, you can see this one that was developed by Andrea itself, and this is a very reduced model that can capture very well the experimental data. So this is a very reduced model, just comprising 20 reactions and 10 species. So the results are actually outstanding. And clearly, I've only talked about single polymers, but we have to account for the fact that we have to extend this to mixtures. And in particular, we have, with the help of the University of Thessaloniki, we actually tried to test our models accounting for mixtures, in particular mixtures of we started with mixtures of polyolefins, so polyethylene, polypropylene, and polystyrene, and we got very good results. You can see some discrepancy, but we are also only talking about 20 degrees, which is actual good results for seeing the difficulty of the problem. And in particular, this was modeled following a completely segregated approach, so neglecting the solubility of the different polymeric phases. Clearly, this is not always the case. We can also model mixtures including PVC, so in a small fraction, accounting for clearly some pretreatment of the plastic feedstock. But clearly, there's some room for improvement, because if we account also for the presence of PET in the mixtures, you can no longer neglect the solubility, for instance, of PET and PVC and the cross reactions between the different phases. So in this case, the completely segregated model loses its validity, and we are currently working on that in order to account these additional reactions. And clearly, as also it was mentioned during the UGent presentation, and the actual reactor is much more complex than a lab-scale setup and the micropyrolyzers. We have additional reactions, in particular in the gas phase. So all the volatiles that are released from the polymer degradation can further react if the operating conditions are suitable, and clearly, since these are big setup, the residence time are usually long, and this can actually favor and enhance the secondary reactions. So what we did, and in particular, was trying to develop some complementary gas phase models in order to account for this additional layer of complexity. Based on the crack model kinetic framework, so basically we have a very general framework comprising kinetic models from the very base molecules, from hydrogen to methane to C4 molecules up to aromatics and soot. And in particular, my work was focused on enlarging this kinetic framework by adding a detailed description of their activity on long chain olefins, which is fundamental to actually predict the product distribution from polyethylene products. In particular, I developed a kinetic model able to describe the activity of long chain olefins up to 60 carbon atoms. And this is actually fundamental because, as we can see, in a very simple setup, such as a two-stage pyrolyzer with a first stage model as a simple TGA, so a simple degradation of the polymer, and a secondary stage for further gas cracking, and without any catalyst, you can see that secondary reactions have a huge impact. As you can see, the dotted lines are actually the results you would obtain if you neglect the secondary reactions. If you consider them, the results are completely different. Only considering the secondary reactions, for instance, just looking at the total gas and liquids retrieved from this simple experimental setup, you can see how the gas, you can see that accounting for secondary reactions, you can actually able to model the decrease of the liquid fraction due to further cracking and the successive increase due to secondary reactions and aromatization. And so, our further question was, what if we consider a more complex setup? What if we consider an actual reactor where the fluid dynamic is not so simple? We have a recirculation, back mixing, temperature profiles. So our approach was, okay, let's consider a bubbling fluid bed reactor, and let's try to simplify it because we are using semi-detailed kinetic models, and how to couple this with computational fluid dynamic simulation. That's basically impossible. It would require too long. So what we did was trying to apply a chemical reactor network approach. So you have a very complex setup. You try to simplify the fluid dynamics through a network of very simple reactors, so either PFRs or perfectly still reactors, according to the validated hydrodynamic of the setup, which, for instance, for bubbling fluid bed reactors is quite well studied. And in this case, what actually is important and matters is the residence time distribution of the gases inside the reactor, and how to be consistent, okay, with our modeling. Okay, so we have a residence time distribution, and we have to ensure that our model is compliant with the actual gas flow pathways inside the reactor. How to do that? I developed an optimization loop which couples the chemical reactor network resolution with a Simulink simulation in which it is possible to perform dynamic experiments, for instance, pulse experiments or stepwise experiments, in order to actually retrieve the residence time distribution inside the chemical reactor network, which is just a representation of the real reactor, and you try to optimize the parameters, for instance, the split ratios, the flow rates, the residence times in order to account for the actual pathways of the gas inside the reactor. And it works. It actually works. You can actually reproduce a residence time distribution, so a network where the residence time distribution of the gas is very similar to the experimental one. This was also validated, I will be very fast because I'm late. This was also validated in terms of results. Clearly, there are some outliers or points which we cannot really explain or expect, but we were actually able to reproduce the trends, the experimental trends, clearly with a certain degree of uncertainty, which actually very typical in this kind of experimental setup, such as three-phase bed reactor. But our main concern was reproducing the trends. So can we reproduce the product distribution, for instance, according to a change of temperature? Yes, we can. And so we can say that not only for a very general reactor, we have a very powerful and effective description of all the kinetic modeling and their activity, but also we can actually tune our reactor model in order to account for all the non-idealities inside the actual reactor. And so we can say that our optimization tool was very well developed. And these are some, the publications that were did in this regard, and that's it. Thank you for that.
Thank you, Chiara. We can now go directly to the next presentation of Coolbrook from you, Tuomas. So about the electrified stream cracking.
Good morning, my name is Tuomas Ouni from Coolbrook, and I'm here today to present the part of Coolbrook in the eLECTRO project. The value chain of eLECTRO project is starting from plastic waste, which is then collected and pre-treated for pyrolysis treatment, which is converting the plastic waste into pyrolysis oil using the electric technology from Pryme. And this pyrolysis oil is then fed into our electric steam cracking technology, rotodynamic reactor as we call it, for conversion into olefins, which are further processed into polyolefins for new plastic products. And we were the leader of the work package number 3, electrified steam cracking technology, development, demonstration, and modeling. Well, 15 minutes is not a long time to explain our technology and all the work we have done in the 4 years of the project. But basically, our technology is replacing the radiant section of a conventional cracking furnace. What that means is that classical steam crackers are working so that they are, the naphtha or the hydrocarbon that is being cracked is flowing in coils, which are heated externally by burning fuel gas or natural gas. And this is done in a furnace type of application. We are doing it differently. We are using a turbine which is driven by electric motor, and this turbine is generating heat with a very high power density. And we are feeding vaporized naphtha and steam into the turbine and cracking the naphtha there within tens of milliseconds, and then quenching the product for stopping the chemical reaction. Our part in the project was not so much to develop the technology. We were rather experimental demonstrator of pyrolysis oil cracking in an electrified way. In the work package 3, the first task was about modeling, but that was mainly done by University of Ghent and AVGI. We were, of course, supporting by giving experimental data, and we needed to do some internal model development to be able to redesign the pilot plant for pyrolysis oil service. The main tasks for us were redesigning the pilot. Originally, we designed the pilot unit here at the Bridlands campus for naphtha cracking. We needed to do modifications on the vaporization part of the pilot and the analytical part of the pilot to be able to handle the pyrolysis oil feedstock. And finally, after the modifications, we were able to demonstrate cracking pyrolysis oil up to 100% in our reactor. We tested many other blending ratios with naphtha as well, and we assessed the product yields, the operability of the unit, and the fouling behavior or coping behavior of the system. Next, we will see a video on the redesign of the pilot that has been prepared by our pilot team, led by Patrick, our pilot plant manager. So here we go.
Welcome at the Coolbrook pilot plant at the Brightlands Gemenot campus. My name is Patrick van der Meer, plant manager for Coolbrook. Behind me, just through the leaves, you can see a glimpse of our pilot plant, which was constructed in 2022. In 2023, we started with our testing program. First, we done a number of heating tests to prove that we can achieve a temperature of 1000 degrees in our system. And after successful completion, we moved to hydrocarbons. Initially, hexane, followed by naphtha. And since then, we cracked naphtha for more than 4,000 hours, proving both functionality and durability of the RDR technology. As a proud member of the Horizon eLECTRO project, it's Coolbrook objective to demonstrate scalable production of pyrolysis oil in our RDR technology. But the pyrolysis oil is a different material than the naphtha we normally use. It has a higher boiling point, it's less stable, and it contains a number of impurities as it's coming from plastic waste. So in order to handle the pyrolysis oil, we had to make a number of modifications to our pilot plant. I'm going to show you these modifications in more details at our pilot plant. Just follow me.
Here you see an overview of the Coolbrook pilot plant. I'm going to take you around and show you step by step how the process works. This is the feedstock station of the Coolbrook pilot plant. 2 containers provide naphtha into the system. We can make a changeover from one container to the other to organize continuous operation.
The pyrolysis oil that's being pumped from the IBCs had to be mixed with naphtha. For this, we created this unit to pump it together with the naphtha into our system. Pyrolysis oil usually consists of heavier components, which could risk fluctuation. To avoid this, we placed tracing on all of the lines, also on the naphtha lines, to preheat the system and heat it up before it enters our process.
The RDR system works with gaseous materials. So our liquid feedstock needs to be transferred into gaseous phase. That's what we do in this preheating station. Kai, can you explain us what the first step is in the preheating station?
Yes, the naphtha comes in through here, and here you see our evaporators. Naphtha usually evaporates between 100 and 150 degrees. But to test the different feedstock, also pyrolysis oil, we had to change it to be able to evaporate up to 250 degrees. So the feedstock mixture together with the superheated steam comes together in another superheater. This is to make sure there's absolutely no condensate in our system. For the eLECTRO project, the temperature of the superheater has changed from 400 to 450 degrees.
The rotordynamic reactor is driven by an electrical engine. This electrical engine, with a power of 800 kilowatts, is combined with a gearbox. The engine can run 3000 RPM and the gearbox can gear it up to 24,000 RPM, needed to bring supersonic speed into the reactor. This is the reactor room where the rotordynamic reactor is positioned. During operation, it's completely closed to create a safe in-earth operation. Kai, our operator, is going to explain about the reactor setup.
As you can see here, we have the rotordynamic reactor our product, our piece of equipment, 2 inlets where our feedstock comes in, makes a bunch of rotations and comes out on the other side. You see a lot of temperature probes, so we can accurately measure the temperature inside of the reactor at any point. And we can use these connections also to take samples of the gas, to analyze the gas inside. Station where we can take our samples from the gas inside of the reactor. It gets cooled, and we have 2 options, taking a liquid phase sample or a gas phase sample. And we can do that at any point on 4 locations inside of the reactor.
Cracked gas from the reactor is fed up here and is cooled on its way. From here, the gas is fed to our analyzer room, where we can analyze online the composition of the cracked gas. Here we are at the analysis room of the pilot plant, where we have inline analysis of the cracked gas.
Here we have 2 gas chromatographs, one to analyze a broad spectrum on hot temperature, 300 degrees, and a micro GC for the smaller components, cooled to 70 degrees. For the electro project, we place an SCD to detect sulfur, because pyrolysis oil contains sulfur.
Kai, you just told us about samples being taken in gas bags. Can you also analyze them here?
Yes, here we created a setup where we can connect these sample bags. As I already said, to the sample bag setting, where we can analyze it from the bag instead of inline from the system.
Shown you around at our pilot plant and highlighted the modifications we made for the electro project. Increase of the temperature in the evaporator, increase of the superheater, and installation of an SCD next to a tracing to heat up the pyrolysis oil. But that was not all. We also had to work on our permit. To run pyrolysis oil, we need to have a modification of the permit. Pyrolysis oil has a specific status within the waste regulations in the Netherlands. So in order to run the pyrolysis oil in the project, we modified our permit with the help of the Brightlands Gemmelot campus, which allowed us to run the pyrolysis oil and complete the project. It was a great pleasure to join the electro project, and we're very proud of the results of the whole consortium.
Thank you, Patrick. That gave you a good overview on the pilot plant and the modifications we needed to do in order to be able to run pyrolysis oil. And some of you will, of course, have the opportunity to see the pilot plant later today. And then the final part of the project for us was a demonstration of the electrified steam cracking of pyrolysis oils into RDR. The testing itself went really nicely, successful and controlled runs. We had full testing of yields and coking rates with 10% and 25% bio naphtha blends. And then we did some additional testing with 50% and even up to 100% bio feedstock. To support the bio testing, we did the baseline naphtha testing at different conditions, varying the temperature, pressure, steam to oil ratio, DMDS injection into the system to really understand how the performance of the reactor is changing with the process parameters. And we completed the process parameter testing in January of this year. And since then we have been working on analyzing the results of the pilot campaign. We have demonstrated the high yields of the RDR technology, which are a result of the very short residence time that can be achieved with the RDR cracking. We analyzed the fouling tendency of the pyrolysis oil based on the results, and a bit surprisingly to us, it was equal to that of naphtha. So adding pyrolysis oil into the feedstock did not increase coking rates in the system, actually included the TLE. But of course, I need to mention here that this was the light fraction of the pyrolysis oil that Pryme gave us. And now what we still have left, I think a little bit still ongoing. It is the benchmarking against conventional crackers in terms of yields and coking, and this is now going on in cooperation with Ghent University. I think Kevin already showed a couple of results, but I think there will be some more to come and to be analyzed. Finally, something about Coolbrook in general. How do we plan to go forward with the RDR technology? So now we think that we have actually achieved at the pilot a majority of the results that we wanted to achieve. Still, of course, a few selected test campaigns to be done. We have proven the rotodynamic heating and cracking principles, demonstrated the benefits of the technology, yield improvement, feasible coking performance, and developed methodologies for continuous operation of the technology, including online de-coking. And of course, most importantly, build good models and design tools for being able to design a commercial scale machine. And now a company is moving on to industrial scale demonstration phase. We have already commercialized our heater technology, which is working with the same principle as the reactor. We have a commercial customer for that, and we are about to deliver a first product to the customer. And this is, of course, one of the pillars for demonstrating the reactor technology as well. Combining the learnings from the heater design with the state-of-the-art chemistry models that we get from the pilot allows us to design the commercial rotodynamic reactor for customers. And of course, we will de-risk it together with the industrial partners. But the final proof point for the technology will be a commercial demonstrator that we are actively discussing with petrochemical partners to have installed in a relevant industrial environment at the moment. And after demonstration of the technology, we plan to scale up the technology globally. We think we will make it de facto industrial standard for steam cracking because of its low CO2 intensity and yield improvement. Probably need to start from geographies with the strongest fundamentals for electrification, meaning basically availability of electricity and renewable electricity, but later on expanding to the rest of the world. And expanding outside liquid feedstocks, for example, gas feedstock like ethane will be cracked in our machine. Yeah, that's what I wanted to tell you today.
So we can now move on to the Engie presentation. It will be a two-voice presentation with first Jeroen for the grid integration and the energy aspects.
So hello everyone, my name is Jeroen, I work for Engie. Maybe first a quick word about Engie. What is Engie? Well, Engie is an energy provider, so it sells electricity, it sells gas. We have a lot of wind turbines, PV panels, like basically everything that produces electricity we have in our fleet. But we also have a lot of plants running on gas. So we have those two expertise. And today I am speaking for Engie Laborelec. What is Engie Laborelec? It's the electrical expertise center of Engie. Later on, there will be my colleague Enrico speaking, and he's more the gas expert. So from Engie UGent. So what did Laborelec do? So as electrical experts, we looked at the grid integration of the RDR. That was one first step. Then once that was done, we selected two potential locations in Europe to install a full-scale plant based on RDR. And then we looked at how do we supply these plants with electricity. And we compute, of course, the cost and the CO2 emission. And Pryme looked at the off-gas valorization, because with RDR, we are using electricity and not the CH4 and H2 that was coming out of the process anymore. We can valorize those off-gases. Okay, so the first part of our study was, okay, we have, you saw the RDR earlier. If you have that at full scale, you cannot just connect it to the plug. So you need a study, and there are some restrictions by law. So we checked, okay, will it be possible from a regulation perspective to connect to the grid? And there, just a quick word, what you want is to have kind of a nice curve coming from the plant. And we checked that, and that was pretty okay. So with a regular RDR, we are kind of at the limit, but there are pretty easy mitigation measures to install if we are just not reaching the regulations. So that was very positive for the RDR grid integration. Then the next step was to define 2 locations to install a steam cracker based on the RDR technology. Here, what did we do? We took a map of Europe. Now you see some small dots. But what we did, we had a dot for each cell of 50 kilometer by 50 kilometer. And what we did for each cell, we assessed what is the renewable potential around this cell, and are there already chemical clusters. And we did some basic math, and then we get a final score. And you see the more red dots had the best scores. And so, yeah, you have a few in Europe, but at the end, we decided to go for 2 locations, one in the south of France. Why? It's because you have good wind and solar potential, so you have this complementarity. And we also went for Roux, because there you have a very strong wind potential. Once we had that, we went to I would say, the biggest part of our work, which was, and I will read the sentence with you, it was to compute the cost optimized. So what do we mean by cost optimized? We look at CAPEX and OPEX spread over the lifetime of the RDR plant. So we compute the cost optimized energy. What do we mean by energy here? Is the electricity you use to produce your or to feed your RDRs and the whole plant. And we look at the supply mix. What does it mean? It means that we start from a blank page and we say, okay, if we want to feed a full-scale RDR plant, we need to install, I would say, 10 wind turbines, 50 solar panels, and 10 batteries. That's basically what we are doing. And we are doing this for, as I said, an electrified steam cracker with a rotodynamic reactor. And we did that for the 2 locations we just selected. So one in France, in the south of France, and one in Finland. It's important to emphasize also that we started with a blank page. So it's not that we said, okay, we can reuse the nuclear power plants already installed, for example, in France, because they are already being used for other purposes. So everything that we are installing is new capacity. Okay. And I skipped the methodology because it's not very complex, but too long to explain. We will jump immediately to the conclusions. So the first important conclusion is renewables are pretty cheap at the end. The problem is you don't have always access to renewables. They don't always generate. So the first key conclusion is it's, at least from a CO2 perspective and a cost perspective, it's way better to start early, even though your solution is not perfect. What do we mean by that? Just install a lot of renewables, and when renewables are not producing, then it's not that bad. We will go to gas turbines and produce electricity with those gas turbines when renewable is not generating. And with that, we already achieve 80% reduction in CO2 emissions compared to conventional steam cracking. And if we look for this mix of generation, we see that so per ton of ethylene, so we took, we did it some months ago, so 1 ton of ethylene we took €1,000, if I remember well, and we said, okay, the cost of electricity to produce this ton of ethylene represents 16% of the cost of today's ethylene. So it's a lot, but it's not that much at the end. From a cost and CO2 perspective, For the energy mix, we also saw it's better to install an e-tracker where there is both solar and wind potential, because you have complementarity. During the summer, you have a lot of sun, of course, and during winter, wind, and you also have that complementarity sometimes between day and night. And that's why, for example, a location as France is better than Finland, for the electricity perspective at least. We are also energicians, so we don't know a lot about chemistry. If you imagine that your steam cracker can be flexible, which means it can reduce a bit the load. We took an extreme case, but if it can do that, we can reduce easily the CO2 emissions to 90% by using renewables. And the cost of electricity will also drop. It will be, the cost of electricity will represent more or less 10% of the cost of your ethylene. And finally, what we also saw is if you put a big constraint, so you want only 100% renewable for your steam cracker, it means that you have to overshoot by a lot your capacity to be installed, because the capacity you install is based on the worst case during your year. And we did the exercise for Belgium, for example, and it represents almost 20–30% of the actual capacity of Belgium. So renewable capacity would be fully utilized to feed only one steam cracker. So it represents a lot of renewables inside the country. So that's also where we align with messages such as Pryme, etc. I think regulations play a big role, and also planification from Europe on that regard. Okay. It does not. Okay. I will leave the floor to my colleague Enrico, who is online.
Enrico Biagini from UGent, so Engie Research Center based in Paris and dedicated to green gases and the energy transition. Our team focuses on how gas and energy can improve industrial processes. So after seeing all the complexity and the effort involved in electrifying this process, can you imagine the waste if we don't use the off gas? So in this project, we studied how to valorize the off gases from the electro processes, and this is the approach we developed for identifying the potential streams, starting from simulation provided by project partner AristEng. We characterized the most promising streams for valorization. These streams are generating cracking, pyrolysis units, and are already partially reused in the process, but a significant share, which is rich in hydrogen and methane, remain underexploited. So their valorization is a key lever for improving circularity, efficiency, and economics. To address this, we designed several process strategies to convert these streams into useful energy and valuable byproducts, either within the process, but also for external market eventually. We then assess their potential uses, market opportunities, and regulatory framework. So finally, we compared all these strategies using a set of performance indicators, and I'll present you in the next slide, please, Jeroen. Thank you. So on this slide, I'll walk you through the results and the main conclusion on our analysis. Starting on the left, we compared, in this case, 4 scenarios. One based purely on off-gas separation of hydrogen and methane, as said before, and 3 based on methane pyrolysis using different technologies. The radar chart shows how this scenario compare across the key constraints we have considered. I'll go straight to the key takeaways of the study. First, the optimal solution is context dependent, driven by local electricity costs, carbon intensity, and market conditions of byproducts. Second, the separation is the most robust and low-risk option, with low electricity needs and capex, but limited in CO2 reduction. Finally, pyrolysis options offer the highest value and emission reduction, but requires favorable conditions, namely competitive electricity, sufficient technology and maturity, viable byproduct markets. So to conclude this short presentation, our study identifies the most promising strategies to valorize all gases in the electro process, assessing them from technical, economic, environmental points of view, and clarifies the conditions under which they become viable, depending on local and global context. Thank you for your attention. Thank you, Jeroen, for helping me in driving the slides.
Thank you.
Next presentation is from AVGI with a techno-economic and scalability analysis. Yes, perfect.
Hi everyone, my name is Ismaël. I'm the modeling researcher at AVGI, and in this presentation I will give a brief overview of the role of AVGI, specifically the techno-economic and scalability analysis. So, short introduction of AVGI. So, AVGI is a Belgian SME. So, our focus is advanced modeling, or advanced simulation and modeling of steam cracking process, also petrochemical processes. So we develop and validate detailed microkinetic models for steam cracking. So this is our team, consists of six people who have actively working on this project, and I'm very happy to present their work today. So the role of AVGI within the consortium was threefold. So we did the Work Package 4 coordination, ensuring that there was close collaboration between the partners of Work Package 4, ensuring that the information between the produced models of the projects were used in the different tasks. Next to that, we did also some technical and simulation work across other work packages, especially Work Package 2 and Work Package 3. And then finally, we conducted the techno-economic and scalability analysis for Work Package 4. So just a few words about Work Package 4. So Work Package 4 is mainly led by 4 consortium partners, Engie, AristEng, Ghent University, and AVGI. So currently there are 3 tasks ongoing, which will be finalized in the coming 3 months. Second part of this presentation will be about the technical work that we conducted, especially for Work Package 2 and 3. So this will be very short due to the limited time that I have to present the work. So first task that we did together with Pryme and Borealis was to look at fractionation. So we developed a rigorous distillation model, both in PetroSim to ensure that we can estimate the utilities needed to do the pre-fractionation, and then a complementary model on a split factor on species level, so making sure that we have an accurate input for the CoiSim model so that you can perform severity optimization using CoiSim. So here we have a figure where you see for both the conventional and the RDR simulation for the different fraction that we simulated. So here we can clearly see the gap that the RDR offers in terms of yields due to the shorter residence time. So the question that we try to ask us is whether it's worth to fractionate raw pyro in different fractions and crack each fraction at their respective optimum, meaning the maximum P plus E fraction. So yes, we see some yield improvements, although they're very modest, and their benefit is outweighed by the high fractionation cost associated to fractionation. Although the answer is nuanced, pre-fractionation might be needed, especially for due to the high final boiling point of pyro, to ensure safe operation in existing assets. Second question that we tried to answer was how much pyro can an existing asset take without running into certain bottlenecks related to incomplete evaporation, coking behavior, excessive condensation, coking in the TLE, and what's the effect on run length. So together with Borealis, we developed a comprehensive full furnace model of their existing assets, and we performed simulations using Coisum for various blend ratios, pyro distillation cut points, and cracking severities. So this is the results of these simulations. So we looked at different things. I will just only focus on the evaporation part in the convection section. So for raw pyro, we saw starting from 10 weight% that we run into evaporation issues. So that the feed is not fully evaporated in the lower banks, leading to higher risk of fouling. You can increase the amount of pyro if you perform fractionation. So if you have a cut point of 450 degrees, you can go higher, up to 30% pyro. Second task that we were working on together with Ghent University was the development of a microkinetic model for pyro within Crexim. So using the single event microkinetic event methodology, we were able to expand our model to accurately describe the thermal decomposition of species within pyro. So for that, we used the information from the other work packages, especially work package 1 and 2, where their detailed analysis about the feed's composition and the molecular species within pyro was used to feed to the network generation. So this model was also validating thanks to data that was acquired in Ghent, LCT, on their experimental setups, and we see a very good fit between the experimental data and the simulations. Next to this, we also developed a low dimensional model together with Coolbrook and Ghent University. So the RDR, in contrast to conventional steam cracking furnaces, has some non-ideal flow behavior that needs to be accounted. So there are some recirculation zone and bypass flows. So we took the approach of a network of CSTRs, interconnected CSTRs, where we can account for recycle and bypass flows. The simulation results for different bypasses are shown on this slide. And we were able, using this methodology, to simulate the pilot plant's data that Coolbrook acquired on their RDR. And here again, we're showing the parity plots, and we see that we can actually very well describe these experimental data. Then the final part is the techno-economic and scalability analysis. So using these models that were developed in work package 2 and 3, we were able to construct the mass and energy balances of the whole plants. So we developed a model within Petrosim, accounting for the different distillations, compressors, and so on. So we also performed a yield optimization for Coisum for different fractions of pyro, trying to achieve the maximum P propylene plus ethylene ratio. So using the results of these simulations, we did some post-processing steps to size the equipment, estimate the capex, and eventually perform a techno-economic analysis. So So as shown on this figure of Coolbrook, the RDR does not combust fuel, so it doesn't have a convection section, which is used to preheat dilution steam, the mixture, and also high pressure steam, which is all eventually used to drive the compressors downstream. So here we have a key challenge. So how can we make sure that the plants or that these two different technologies can operate well with the overall plant? So therefore we develop different integration configuration together with our partner Coolbrook, which are summarized here. So in short, they're just different in how compressors are driven. So we have different configurations where the compressors are driven using high pressure steam or electricity, and then another key difference is the high temperature preheating of the steam hydrocarbon mixture. So all these configurations were simulated, and the energy and mass balances were calculated. One of the key results that we saw is that to feed a world scale ethylene plant, we need about roughly half of the available waste in Europe. So pure pilot cracking is very unlikely. So therefore, it's also important to consider cases where pilot and naphtha are co-cracked. Then we also did some techno-economic analysis. I think, steam cracking is a very high energy intensive process, so the energy price is very important. So we looked at the electricity price versus the fuel gas price, and we calculated the break-even points. So at which point does the RDR and the conventional steam cracker lead to the same economic performance? And depending on at which scenario we're looking at the electricity price, the RDR has potential to outperform conventional steam cracker. But this is a relatively low electricity price, so only in optimistic scenarios this overall concept can compete. Next to this, we also looked at the difference between naphtha cracking and pilot cracking. So we saw that to have a break-even, we need a premium for recycled content, which is about 2.5 or 3 if you're very strict about your definition. If you only conclude ethylene and propylene, you need to factor 3 premium price for these products. And then finally, we also looked at the economic evaluation in defined as here as payback time, so in favorable market conditions, so including a favorable outlook for your electricity price, and assuming that you get a premium for high-value chemicals, we see that the concept is actually very attractive compared to conventional steam cracking cases. Right, and then AVGI also took, participated to several conferences where these results were disseminated. That was my last slide. Any questions?
So what is now the main contributing factor to the OPEX that you have? Is it the electricity price, or is it something else that drives the main cost?
The main cost driver both for the RDR and the steam cracker is the feedstock price. Electricity price, I don't remember the number, but I think it was around 20%. Of course, depending on the scenario, depending on the output price of electricity.
You showed those scenarios about the electricity becoming optimistic to realistic to
conservative.
Did you include CO2 price in your calculations?
Yes, but we saw that the CO2 pricing is actually not the main contributor. So we'll have to go to very high CO2 prices to actually make a dent in your
economy. CO2 was used for fuel, but not electricity was assumed 100% green.
Yes. We didn't really assume. well, this is part of the life cycle assessment where this is taking a look at, and that was part for our partner AristEng. So we didn't really look at the origin of electricity. So, well, if we look at CO2, it's mainly scope 1, so whatever is exhausted within the plant. We didn't look at the other scopes for your CO2. So this electricity could be, yeah, just grid electricity. It's just the market price that we're looking into here. All right, thank you.
We are now going to the AristEng presentation with Amvrosios regarding the LCN process optimization.
Well, AristEng was responsible for 3 tasks, tasks for 2, for 3, and for 4. Tasks for 2 and for 3 have been completed, and the only remaining unfinished task is task for 4, the environmental assessment of the electro process. Of course, deliverable is scheduled for submission within the agreed time frame by month 48. Also note that to proceed to the LCA analysis, we needed mass and energy balances. These balances were obtained either from simulations, for example, AristEng developed in-house codes for process design, or as inputs from partners. So what we did, we investigated 3 process alternatives and 10 scenarios by comparing different configurations, electrification levels, electricity sources, and CHP fuels. As a reminder, in decentralized configurations, we had 2 locations. The pyrolyzer was a different location than the e-cracker, and the bio-oil should be shipped from location 1 to location 2. On the other hand, in centralized configuration, all units are co-located. For CHP powered scenarios, we have a combination of 5 heated sources and electricity, either from grid or the wind. And for the fully electrified cases, we relied only on electricity, again, either from the grid or from wind. Also notice that the centralized configurations differ in CHP fuel management, decanted oil versus solid residue. So we assessed 16 impact categories using the commercial software CIMAPRO across all scenarios from scenario 1 to scenario 10. And for now, results have been collected, but are currently being processed. Once this procedure is completed, we will upload the updated database on eLECTRO as well. However, during this presentation, we will focus only on the climate change impact for comparing the environmental performance, and we will also present an uncertainty analysis using Monte Carlo simulations to assess the reliability and robustness of our results. Let's start with the deterministic results. Deterministic means fixed inputs, and the model produces just a single result. So these are the GHG results expressed per ton of mixed plastic waste, together with the relative contributions of scope 1, 2, and 3. However, these trends are easier to see in this slide, and actually the trends are quite straightforward. We can see that the CHP-powered scenarios that combine 5 heated sources and electricity are dominated by scope 1 emissions, the red bar. Switching to the fully electrified ones, we can see a shift to the burden to scope 2 emissions, and the combination of full electrification and renewable power delivers the lowest GHG emissions, scenario 4 and scenario 8. Also note that for scenario 8 and 4, we can see that the contribution of mixed plastic waste increases to almost 30%. This is a key point during this presentation, so keep that in mind. So let's move to the uncertainty analysis. As I said, we use Monte Carlo simulations, but we will focus, due to time limitations, only to scenario 3 and 4. So, to assess the robustness of the results and the reliability of the results, a Monte Carlo analysis was performed using 2,000 iterations, using in-house codes. Uncertainties were applied to grid electricity emission factor and grid electricity emission factor, to the electricity demand, and to the distances of mixed plastic waste transport and oil transport. Note that all the simulations were performed simultaneously. Also, uniform distributions were used when values within a known range are considered equally likely, and log normal distributions were used to ensure positive quantities. Let's start with scenario 3, the decentralized fully electrified scenario powered by grid electricity. Note here that the Monte Carlo analysis considered uncertainty associated with the emission factor of grid electricity across potential EU deployment locations. So actually we performed a geographical variation here. And results show that 90% of the predicted GHG values lie between 211 and 2,222 kilograms CO2 per ton of mixed plastic waste. This slide summarizes the uncertainty results of this scenario and shows that the grid electricity emission factor is the dominant driver of GHG emissions and uncertainty, with a value almost to 1. We have seen that country-specific electricity mixes are the main source of uncertainty, with Sweden and Poland representing the lower and upper bounds. Also note that this distribution is quite wide due to the larger upper bound. It's almost 35 times higher than the lower bound. And this is scenario 4. This is the fully electrified scenario powered by wind electricity this time. Here the Monte Carlo analysis considered uncertainty associated with the emission factor of Dutch onshore wind electricity. So we're talking about a system-specific approach here. And results showed that 90% of the predicted GHG values lie between 70 and 178 kilograms CO2 per ton of mixed plastic waste. Of course, here we have reduced uncertainty compared to the previous scenario. And again, this slide summarizes our results, our uncertainty results. We can see here that when using wind power, mixed plastic waste transport distance becomes the dominant driver of both GHG emissions and uncertainty. And actually, this is a key observation because it actually corroborates the results found during our sensitivity analysis. That we had also seen that mixed plastic waste transportation is actually the main driver of GHG emissions. So this is a very nice result because it corroborates this finding. And many of you are also know this finding because we will present it in our upcoming manuscript. And that's all from our side.
So the next presentation is from UGent with Kasper online about the societal cross-cutting issues.
Hi everyone, I'm a postdoc from Ghent University. I just wanted to say I'm really sorry that I'm not there. It's a pity to miss the face-to-face discussions, but I'm still very happy to present online, and I look forward to receive all your critical questions afterwards. In the eLECTRO project, I was responsible for developing a plan for integration, for the integration of societal cross-cutting issues. And this plan should include goals, actions, as well as a division of roles and responsibilities. Next slide, please. And to develop this plan, I actually mobilized the field of socio-technical integration research. Just a small disclaimer, the upstream, midstream, and downstream on this slide have nothing to do with the petchem supply chain you all know, so forget about the supply chain for now. So I mobilized this framework, and upstream or integrating societal issues in the upstream means that you develop innovation policy in order to steer in which direction technology should be developed. For instance, in the direction of tackling the huge amounts of plastic waste. But these innovation policies are often very vague. too vague actually to already include concrete societal considerations, as we don't know yet what the technology will eventually look like. So in this upstream, we actually often intervene too early in the technology development stage to integrate societal issues. On the slide, you also see there's a downstream. So here the technology is already developed. It has a high TRL. And then you actually, as an engineer, for instance, you go to society and you ask society to accept your technology. You ask a policymaker to fund, de-risk, or regulate your technology. A recent example was given this morning by Kevin. He said that there should be legislation in the context of the mass balances of pyrolysis oil. Now, this process evolves very slowly. I would argue that the slowness can be explained because societal actors are currently resisting this particular type of technologies. So actually here we see that we're intervening too late. And if we would have intervened earlier, there would have been less resistance. And that is why actually in the eLECTRO project, I focused on the midstream. This is the R&D phase of technology, the technology development phase. eLECTRO is in the midstream. And here you actually do not intervene too late, neither too early. You're still flexible to include societal considerations in the technology. So this is very much an overlooked opportunity. Next slide, please, Jean. So what I found when I analyzed eLECTRO's midstream is that the integration of societal aspects is actually will actually be highly challenging, especially to engineering scientists' alignment with industry and entanglement with industry. There is a very high focus on efficiency and on business cases as well. There is a belief in technology as good for society as it reduces emissions. And there's this perceived role as scientists, as providers of neutral knowledge for better decisions. And these four aspects actually make it very challenging to integrate societal issues in projects such as eLECTRO. And actually, there's a paper forthcoming on this topic soon, which I wrote with Gert Goemene. Next slide, please. Next slide, Sean. Thanks. Given the engineering scientists' particular perceptions about their own roles, about their own responsibilities, I found that it's going to be very challenging. And actually, this perception resembles the much criticized and debunked linear model of innovation. Like in normal terms, this linear model claims that my science and technology will lead to a better society. So the perception within eLECTRO very much resembles this model, and it actually constrains more responsible research and innovation models. And this makes integration challenging. And here I found actually that eLECTRO will need a very specific socio-technical integration plan, which I will detail in the next slide. So what I did is actually define particular roles, responsibilities, and tasks for the different actors within eLECTRO. For social science and humanities scholars like myself, the plan implies that we should take the concerns of engineering scientists seriously. These concerns are really a collaboration opportunity rather than a threat. We should also really ground our work in engineers' everyday practices, their live worlds, within your labs, within your funding mechanisms, and so forth. And we should also engage in a generative critique. So this means we do not provide you with uncritical research assistance to legitimize your technologies, but we also do not provide you with like this detached armchair critique without providing you with any actionable aspects to deal with in your concrete practices in the lab, for instance. Next slide. For engineering scientists, the plan implies that you have the responsibility to observe, analyze, and then reflect on how and with what kind of awareness you are doing what you're doing every other day. And the plan also implies that you should enhance your science, technology, society relations literacy. This, for instance, implies that you get to know what the linear model of innovation is, and that you get to know other models like the responsible innovation model. Next slide, please. For project coordinators and science policy stakeholders, my integration plan implies that these actors should provide support, financial, institutional, intellectual, for integration efforts. They should facilitate humility on the part of both engineering scientists and social scientists. And they should be attentive to power dynamics between, for instance, disciplines in terms of resources, so financial resources, that is, in terms of power to set the agenda, in terms of power attached to knowledge and the legitimacy of particular types of knowledge, but also very concretely, for instance, in terms of the distribution of time for presentations. It's quite obvious that today I only got 5 minutes, while all other partners got 15 minutes to present their work. So this is something project coordinators should be attentive to. Next slide, please. And in conclusion, I would say that my plan outlines very actionable roles and tasks. We can actually start working on them today. So it's very actionable also for the actors within eLECTRO, but also for actors in other projects that resemble eLECTRO. If this plan is implemented, and that's not only my task, I think that's quite obvious by now, I think eLECTRO's technologies will be more responsible and socially robust. And then I just wanted to say that I really look forward to experiment with these new roles and responsibilities in future projects, and to investigate what enables and blocks these new roles. So thank you for your attention, and thank you for involving me in this project.
So first of all, I would like to thank all of you to join here for this event. Also the people online for following us also during the project. So thank you for coming to here in this exceptional conditions as well. I want to thank Patrick for organizing this. He put a lot of effort, not only for arranging for the rooms, for the food, and for organizing the visits that will come. So thank you, Patrick. I think we have to give him a big hand. As a project coordinator, of course, I cannot do it without everybody here of all the companies and all the partners. So thank you all. It was a pleasure to work with you. So thanks again, and really it was an incredible journey that we did together, and I'm still very proud, and I'm still aiming for a science paper. I really believe that the data that we have are so good that we can submit a paper to science, and we will for sure try that if my agenda survives it. But okay, we will find a solution. The data are there, they're very unique. And I think that's work for the coming 6 months, is to summarize this in an incredible publication that we will try to get there. Last but not least, of course, Jean, I want to thank you for helping us from Bankay's side. But we need to thank Elisabeth. So Elisabeth did all the work in the background. Always helping us, pushing us on the right moments, especially pushing me. But it's a pleasure to work with you, and without you, this wouldn't have resulted in these great results.